and welcome to the new chapter of control. So in this chapter, we would like to talk about a new idea that actually can help us in order to some kind of make our life a little bit easier. Because if you remember, for the last some kind of section, we were talking about the reduction method that actually we can just make all of those complex situations to one reduced one that actually at the end of the day we can use it for a transfer function. But obviously, not all the works that we are doing or not all the math that we are using for the block diagrams are going to be easy. That's why today we are going to introduce a new model that we call as a Mason model in order to use it. And at the end of the day, instead of just doing all of those calculations and all of those consideration, you can use it in order to make our life, again, a little bit easier. Without further ado, let's talk about it. As I just mentioned before, we are going to talk about the block diagram reductions. Because if you guys remember, for the previous part, we talked about this legacy way approach of the block diagram reduction. It means that if our system getting too complicated, you have to deal with all of these some kind of diagrams over here from the beginning to the end to just find the relationship between output and input. And as you can see, if your system getting complicated, you have more than 2 or 3 paths, you're getting lost so easy, and it obviously takes a lot of time. The modern alternative, which we call as a Mason rule, is a new way that actually can help us in order to reduce all of those complication method into something way better. So before just talking about that, before just talking about the Mason rule, let's have a little bit review at the anatomy of a signals flow graph. So as you guys know, we do have the very first guy, which is going to be our source node. Obviously, at the end of the day, we would like to find the relationship between R and C, output and input. But the important part is whatever is happening between them. So R is going to be our source nodes. Whatever input that you have, you're going to put it in that side. G1 is going to be branch, is going to represent the transfer function or gain. It could be anything. It could be a number. Again, it could be in a Laplace form. Again, we are going to work in Laplace form because, as you guys just told you, working in the time domain would be a little bit complicated, but at the end of the day, we have to convert the Laplace to the time domain because that is important. Then we do have the E is going to be considered as an internal node. So as you guys know, we do have this node in order to see that whatever comes inside of that and whatever feedback loop that we do have, those guys have to be combined to each other and then should move to the output part. So again, the G2 could be another branch that has a different gain. The X is going to be just a normal node that is going to be the G2 and G3 actually are going to be the same, because whatever is getting inside of that node is going to be happening outside of that. The G3 is going to another branch and C is going to be my output. So if I would like to somehow make this node or find the relationship between input and output, somehow I can simplify it to the E, which is going to be very, very important for our internal node because it contains a feedback loop as G1 times R plus H times C itself. So this is a very classic way. By finding the E, and after that you can write down the C based on the E and write down E based on R, you can find the relationship between input and output. So right now it's not that kind of complicated because you only have one path, which we call as a forward path, and you have one only feedback loop. So everything is fine. But just before talking about the Mason rule and why we use that, let's talk about another analogy, which we call it as path and loops. Again, this is not that kind of a new thing because we know most of them, but I would like to put my focus on the non-touching loops, which I'm going to talk about it in a little bit later. The very first one is about the forward path. What is forward path? Forward path means that whenever you're moving from one specific point, for instance, at this case, I do have my input, whatever path you're choosing should only move forward. You don't have any backward condition. For instance, at this case, I do have G1 times G3, which is going to be my forward path. I do have H, which comes from R to the C or from input to output as my another path. But I cannot consider this guy as my path again, because as you can see over here, this guy is moving back to the R, which I don't like it. So again, at this point, I do have two forward paths, and the flow from input to output and following a branch directions can be considered as a forward path. Again, we are not going to visit the same node twice. Whatever is happening, just one node at a time, and we are not going to come back. Another thing that we do have, we call it as loops. So obviously loops, as you guys know, means that I do have the forward path, but again, I have to come back to the node that I started. So this guy can be considered as a one forward path. this guy and this guy can be considered as another loop. So for I do have two loops. One of them is going to be G2, G3 times H, and another one is G2, G3 times another H. So at the point when I do have H1 and H2, obviously these two parts are going to be different. So again, the closed path starting and ending at the same node. So at this point, we do have the gain, which is a product of all of branches in the loop itself. Important thing that we do have is about the non-touching loop. What's this non-touching loop? Means that you do have various loops, obviously, for your work, but at some point you can see over here that these two loops, they are somehow sharing the same node, right? One of them is going to be over here and another one over here, but still they're sharing the same node or same somehow gain at this point. It's a gain because of the branch. But at some point we do have two loops that they are not going to touch each other, that we call them as non-touching loops. It means that those guys are not going to share absolutely no common nodes. At this point we don't have any non-touching loops, but I just gave you the definition of what was that, and in the future we are going to touch that a lot. So let's talk about the Mason gain formula at this point. What is that? Why we are using it? So as you guys just saw from the beginning, everything was simple, right? I mean, you do have forward path, you do have one loop, and obviously you can find the relationship between output and input easy. But imagine that your system is going to have more than one loop. It has two or three or more than one forward path. So obviously finding the relationship between output and input is not impossible, but it's going to take so much time. Why we use the Mason rule? Because Mason rule is going to help us in order to somehow reduce the amount of calculation, reduce the amount of time that we would consider for solving a question, and obviously at the end of the day reduce the amount of number of errors that we do have related to that. So the Mason rule says that the transfer function, which is going to be the final t, is going to be 1 divided by delta. We do have two different kind of delta. The very first one is just normal delta. It doesn't have any index, but another one is another delta that we call as delta k. I will talk about all of them in detail, and we are going to solve a couple of questions that you're going to be familiar with it. Don't worry. The very first delta has this definition, which is called it as the system determinant is going to be 1 subtracted by sum of loop gains. As you guys, for example, saw in the last part, we had one loop gain that we called as G2, G3, H1, and another one G2, G3, H2. 1 subtracted by sum of all of these guys plus sum of non-touching pairs. Imagine that you do have two some kind of non-touching loop, for example H1 and H3. Whatever gain that they do have, you have to multiply it by each other, subtracted by non-touching triplets. So at this point, at some case we do have the pairs, but at another case we do have, for example, 3 loops that are not touching each other at all. This is very rare condition, but you have to consider it. So at this point we know what is delta. What is tk? Tk means that gain of the kth forward path, because as you just remember, we at some point we have one path, but at another forward path, by the way, but at some point we do have maybe more than one, so we have 2. That's why we do have different gains, and we have to multiply by what? By delta k. The delta k, it's what? It's going to be as the path cofactor. It means that the value of delta with all loops touching the k path removed. It means that this value is going to tell us that how many of these forward paths that we consider, or some kind of how many of loops that we consider, are going to actually be there if we remove the whole forward path. If you do have a couple of them, it means that your delta k should follow another formula that I'm going to show it to you, but most of the time when you get rid of the forward path, there's nothing there, because everything that you had was related to the loops actually is gone. Why? Because the related node is gone. So you just assume that delta k is 1. Delta k is 1 is a very, very common some kind of number that we would consider that. And if in the future we see that if we remove the forward path and we still have something, we have to consider that one as well. So this is going to be a very, very simple matrix related to the blocks, the formation blocks to branches. Imagine that you do have the signal lines. In the traditional block lines, we just call it as like this. But every signal at this point, they are going to become a node in our modern SFG equivalent. Then we do have what? We do have the blocks that we saw it as G. So at this point, these guys are going to become branches and branches, they do have gain, which is important to us. Then we do have the summing junction at the very first example. You guys remember I was talking about E, but at this point, these guys are going to be, again, the summing junctions are going to be, again, nodes, and we do have the negative feedback, and this guy is going to be into the branch gain, as you can see over here. But very important part is about the sign of the feedback gain. So as you guys know, the feedback gain, if it's going to from the output again to input, means that we do have the negative feedback loop. If it was the forward path, which we don't consider it as a loop itself, by the way, it's going to be positive. So this is very important. It's not that kind of in detail characteristic of the model that we are using for the Mason rule, but it's going to be a path. So again, the Mason algorithm works like this. The step number one is that I have to identify all of the forward path. Again, what is the forward path? Means that if I start from the beginning, that most of the time is R, to the end, which is C, how many paths can I go there? For instance, if I would like to go from my house to a supermarket, how many forward paths do I have? Again, by forward path means that I cannot go back. I have to only move forward. So by this guy, I do have my T case. Then I have to identify all of the loops, or all of the loops that which loop consider a forward path and another way that comes back again to the first node itself. Then I have to find the non-touching pairs. Most of the time they are pairs, but if you find the triplets, that's good. So the pairs means that there should be two loops that actually they cannot touch each other, or they don't touch each other. Why? Because they don't share the same node. And then we have to compute the system determinant. If you remember about the big delta, or the delta one subtracted by sum of all of those gains plus multiplication of those non-touching gains that I will show it to you. Don't worry about it. And then we have to compute the path cofactor. That was delta 1 and delta 2. Most of the time would be just 1. And finally, I can find my T, which was a formula that I already showed it to you. So at this point, I would like to solve a question, and I would like to solve this question based on two ways. The very first way is just a normal way that we used to know, and the second one is about the Mason rule. So let's talk about this one. What is my end goal? The end goal at this point is that I would like to find the relationship between C and R, which is considered as my transfer function. So I have to find the C divided by R. The very first thing that I have to do is I have to start from the end to the beginning. Why does it mean? It means that first of all, I have to see what are the signals that actually getting inside my C. I don't care about the output, because output is just a normal loop. I just do care about all of the signals that actually comes inside my C. So at this point, you can see my C. You can see that my C letter contains only one branch, which is going to be like this. It means that whatever is happening inside the E node multiplied by this branch is going to be my C. So if I assume that my G is going to be 10 divided by S plus 2, I can multiply it by E. Am I done? Obviously not, because I would like to find the relationship between C and R, not C and E. So what is E? E, I have to again look at whatever signal that comes to it. If I assume that R is my input signal multiplied by the gain that it has based on the branch itself, which is 1, E is goes to be R plus whatever that comes from the C itself. So at this point, you can see that I do have the feedback loop, and this guy is going to be 0.5 times whatever that C was. So what should I do right now? The only thing that I have to do, that instead of this E, I have to find a new value and put the R plus 0.5 C there, and then I can do the calculation and find the relationship between C and R itself. Just right now, you can see that how much complicated my calculation could be just by having the normal notes. Yeah, well, maybe some of you would say that, okay, at the end of the day, I can solve it. Yeah, I know that is obvious. But what would happen if rather than E, you had another part? What would happen if rather than H, you have, for example, another two loops? What would happen if your path is going to get bigger? And obviously, what would happen if you have more than one path? You have to consider all of it, right? That's why we do have the Mason rule. So Mason rule would says that we had to go based on the algorithm itself, but obviously if you solve a couple of questions, you can get it so fast. But let's start from the beginning. The very first important part is about the path, or the forward path. First of all, we have to identify all of them. How many forward paths do we have? Obviously, as you can see, if we follow this one, and yeah, let me use another color that will be way better. If we follow this one and this one, we do have only one forward path. There's nothing there that actually we can guide us from input to output. So my gain, or the very first one, is 1, and another one is g. 1 times g is going to be 10 divided by s plus 2, that is t1. This is a forward path. What is my loop over here? Loop is whatever this guy is showing it to me. As you can see, just obviously loop. It moves from E to C and then from C to E again. But one important thing that I just told you that we have to consider, that for the calculation, we have to consider the loop sign. So at this L1 is going to be what? Is going to be G times H itself, right? Is going to be negative 5 divided by S plus 2. Why negative 5 divided by S plus 2? Because obviously if you multiply 10 divided by S plus 2, but H is going to be 0.5 itself, at the end of the day, you have that some kind of specific fraction by considering the fact that your loop or your feedback loop is negative. So we have to construct our delta, right? As I just told you, the delta itself is going to be 1 subtracted by the summation of the feedback loop plus multiplication of non-touching loops. How many some kind of feedback loops we have? Obviously only 1. How many non-touching loops you have? Obviously nothing, because as you can see, there's only 1 loop, so there's nothing there that I can compare my 1 loop to another one. So at this point, I do have 1 subtracted by L1, which my delta, if you guys remember, that delta was in the denominator, that my delta is going to be 1 plus this one, and I do have this fraction. So at the end of the day, I can solve it. But another important thing that just left is about the delta k. So why my delta k doesn't have anything to do with here? Because imagine that you do have the forward path, and delta k is going to follow the algorithm, and that algorithm would says that, okay, get rid of your forward path, and then you can see that your delta k is there or not. So delta k is something related to the feedback loop. And if you get rid of your forward path, it means that you're doing something like this. Let me, for example, use this color. It means that you're getting rid of this guy. And then you are going to see that, okay, what is happening to my feedback loop, which your feedback loop was something like this, right? But as you can see, something is missing. I don't have E and I don't have the C anymore. So it means that if I get rid of the forward path, my feedback loop is completely meaningless. At this point, we assume that the delta K is going to be 1 and we can move forward from that point. So my delta K is going to be 1 because the loop touches the path. So this is a very, very good practice for you, that if you would like to see that what is the number for delta K, you have to see that either the loop is going to touch the path or not. If it touches, it means that your delta K is 1. If it doesn't, we are going to show you a formula that actually you can find that one. Most of the time is going to touch that one. So my formula T is going to be T1 because the sigma of Tk times delta K was 1, and my Tk which was a forward path, was only 1 forward path, and the delta, which is the one that we just calculated, is going to be like this. So T1 divided by delta is going to give you something like this one, and if the question asks for the DC gain, it means that your S is equals 0, you can find it. So at the very beginning of the point, maybe some of you would say that, okay, it doesn't make any sense, because first of all, we have to learn something, and then obviously I have to do all of the calculation. But as you can see over here, this guy is not going to show you the advantage or privilege of the Mason rule against the normal schematic one. But in the future that I'm going to show you more complicated question, you guys are going to literally see that why we like the Mason rule. But right now, let's just learn it. Let's just try to compare the schematic and the calculation engine. Obviously, you have to do that to make sure that everything is going to right, and both of those answers, which should be the same itself. So let's move forward. Let's see actually a more complicated question. So imagine that right now you do have this guy. So obviously, you have to compare the value of this one or find the fraction between this guy, which is one is the numerator, and this guy is the denominator. And after that, you have to find your transfer function. Obviously, it would be so complicated because of why. At the first one, if I do need my output is related to this guy is related to this guy is related to this guy, and this guy is related to this guy. You have to do it 4 times. At the end of the day, you can find the relationship between output and input. Obviously, it's not feasible. That's why we are going to use the Mason rule itself over here. So I do have the system and the values are like this. Again, I didn't want to make it complicated. That's why I only used the numbers. So G1 is going to be 2. I mean, you can find it over here, by the way, but I'm writing it down for our ease. And G2 is 3. I'm sorry, G2 is 3, G3 is 1, G4 is 4. Then I do have the H1 is going to be 0.5. Again, don't forget while you're doing or using this number in your calculation, you have to consider the negative sign. And the H2 is going to be 0.25. So as we just told you, first of all, we have to find a path and loop. So the very path that we do have is going to be from the beginning to end. It's easy. The G1 times G2, G2 times G3, and G2 3 times G4. Do I have another one? No, because H1 and H2 are the loops and they don't see any forward path to me. So that is simple. My T1 is going to be 24. How many loops do I have? I do have obviously H1, obviously not H1 just by itself, G2 times H1 and G4 times H2. Again, be careful while you're doing the calculation, you have to consider the sign. So it would be a good practice to consider the sign at the very beginning. So L1 is going to be 3 times 0.5, negative 1.5, and L2 is going to be G4, which is going to 4 times 0.21, is going to be negative 1, again with the negative sign. So the delta expansion. So at this point, I have to find the delta itself. As you can see, my delta is a little bit bigger this time. Why? Because I do have 2 loops, unlike the last one, and I do have 2 non-touching loops. Again, this is a good practice to see that what does it mean by non-touching loops. So as you can see, I do have 1 loop, which is this big guy, and this another one, which is another big guy. But these 2 guys are not sharing the same node. Yes, in the same path, maybe you would see that those guys are somehow connected to each other. Maybe some of you would say that, okay, this node is actually this one because my gain is 1. But this is not how this guy works, because at the end of the day, the formula itself is going to consider that. So at this point, I do have these 2 nodes, which is related to 1 loop, and I do have another 2 nodes, which is related to another loop. So I would consider the H1G2 and H2G4 as 2 non-touching loops. So my delta would be like this: 1 subtracted by summation of all of those loops that I have, which is this guy and this guy, plus the multiplication of non-touching loop, which is this guy and this one. So delta is going to be 1 subtracted by negative 1.5 and plus negative 1, which is like this, and the multiplication of negative 1.5 and negative 1. So my delta is going to be 5. Another important thing is about the delta k. So because as I just told you, delta k works on a time that when you get rid of your path itself. Obviously, if you get rid of this path, you see that our loops are going to be completely meaningless. So delta k is just going to be 1 itself. That's why you don't have it over here. So at the end of the day, your transfer function is going to be T1, which our forward path times delta k, which is 1, so we don't consider that, divided by delta. We found it, and after that, we do have 4.8. You just see that how this Mason rule actually makes our life much more easier. Because if you would like to consider the fact of using the schematic model or normal model, you have to some kind of find this guy based on this one, this guy based on this one, based on this one, based on this one. Again, move forward for all of them until reach to the output, and after that, find this relationship with input itself. So let's see the part that actually would be a little bit more complicated. So imagine that you do have a system like this. So multiple forward path, because most of the time that for the last 2 examples we talked about it, we just assume that, okay, we only have 1 forward path. But as you can see over here, we do have more than 1. Why? Because at this point, I do have my G1 and goes to G3, and then I go to output, and then I do have G2 times G3. So obviously you can see there are 2 forward paths. And then my T1 is going to be G1, G3, and my T2 is going to be G2, G3. But how many loops do I have? This is obviously a 1, because G3 times H, which I have to consider the negative sign. So let's solve this guy. At this point, I'm going to get rid of that since you already understand it. My G1 is 5, my G2 is 3, my G3 is going to be 1 divided by S plus 1, and my H is going to be 2 itself. So what is L1? L1 is my first loop. What is that? It is G3 times H while I consider the negative sign. So G3 was this guy, and my some kind of the H was obviously just 2. So my L1 is going to be negative 2 divided by S plus 1. How I can find the delta is going to be 1 subtracted by the summation of all of those feedback loops, which I only have 1, plus the multiplication of feedback non-touching loops, which I don't have any, so I don't care. So my delta is going to be 1 subtracted by what? Subtracted by G3 times GH, actually negative sign. So at the end of the day is going to be like this. What about the delta K? As I just told you, for the delta K, which is related to the for my forward path, if I get rid of the main path that I do have it over here, I don't, my some kind of the feedback loops and my some kind of the G1 and G2 are going to be meaningless. Since those guys are going to be meaningless, or since my loop is going to touch both paths, I can say that, okay, delta 1 and delta 2, which is related to delta K, is going to be 1. So the collapse, and so I'm going to find out that at the end of the day, my T is going to be like this. It's going to be T1 plus T2, delta K is 1, divided by delta, and I do have something like this. Easy. Very, very easy. So before talking about, again, talking about the future part, at this slide, I would like to talk a little bit more in detail about the delta K, because most of the time it sees that, okay, this is 1, but what is actually that guy? So imagine that you do have the full graph like this. So you can see I do have G1, G2, G3, G4, H2, H1, and there's another thing that is happening over here, which is completely separate from the system. So when we do have the path isolation, when we do have the forward path, it is easy. I only have one forward path if I consider that one. So G1, G2, G3, G4. This is my forward path. We are going to assume that the signal fully occupies this chosen forward path. In order to find the delta K, we have to have the next step, which is the deletion. And that this deletion, you can see that H1 and H2 actually are gone, but H3 is already there. So since this guy doesn't have anything to do with my forward path, my delta K is not going to be 1. My delta K is going to be 1 subtracted by negative of H3, which is going to be my feedback loop, or which is going to be completely out of the scope. So what is the truth over here? The delta K is actually the residual topology, but residual means that we have to get rid of the forward path, and it represents the dynamics of the system that remain active when your chosen forward path is fully occupied. Obviously, you can see if you get rid of your forward path, H1 and H2 are already gone, but H3 can also be being functional there. So by calculating delta K, Mason rules isolate the structural dynamics without requiring you to some kind of redraw a single line, and that is a beauty of the Mason rule. So let's see an actual example. Let's see a very, very good example that I love it, because right now you can see that how actually Mason rules works. And what we do have the full package, we do have the forward, we do have the feedback, and we do have non-touching loop, which at the very beginning maybe is going to be a little not visible, but we are going to talk about it. So imagine that you do have this is a real world example, real world deployment. You do have the aircraft pitch control. And at the end of the day, they're asking, what is the transfer function? What is the relationship between input and output? So you can see I do have one node, and then I do have my first gain, then I do have another gain, and I do have the output node, then I do have H1, or it would be better to say GP times H1 as my one loop, and then I do have another loop. Actually, it's not hidden, but it's going to be a little not obvious. So I do have this guy multiplied by this guy multiplied by this guy, my second loop, and then I do have another feedback loop, which is going to be very important, because again, at the first glance, maybe you guys not see it. It would be this part multiplied by this gun, and then multiplied by this gun, and goes back to this. That is very important. And at this point, I do actually have the non-touching loops. Why? Because at this case, I do have this guy, which is going to be one loop, and I do have this guy, which is going to be another loop. Maybe some of you would say that, okay, what's going on over here? Because the way that I see it, these two guys, which is going to be the big one and a small one, they actually have the same node over here, but it is not. Because as you can see over here, the output is over here while this node is here. So obviously we do have something at this point, which could be nothing. But if you guys remember for the previous path, I told you that even if the gain is 1 over here, my output comes from this side. It didn't come from this part. That's why I do have this guy as one non-touching loop, and I do have another guy which is like this as another non-touching loop. So let's just solve this one based on these values that we do have over here. So let's just write down, that would be way easier. GC is going to be K. Oh, not this guy. I'll probably have to use this one. GC is going to be K. Then I do have the GP is going to be 10 divided by S, with 10 divided by S times S plus 5. Then I do have the H1, which is going to be 0.5S.
the GFF is going to be 2 and H2 is going to be 1. By the way, guys, I really recommend you to stop your some kind of video right now. Try to look at the question by yourself, that see if you can solve it or not. At this point, I'm going to solve it step by step with you, so don't worry about it. But again, stop the video and make sure maybe you can solve it and you can come back later. So let's look at the question. So for the very beginning step, as I just told you, before finding your path and all of those feedback thing and mumbling and jumbling, is just writing down the formula. My t, or the final transfer function, is going to be the sigma tk times delta k divided by the whole delta. So you know that we do have a full package, we do have non-touching loop. Obviously delta k is going to, it is going to, maybe it's 1 or maybe it's not, we don't know right now, because we have to get rid of the forward path and see actually our gain is going to be related to that or not, which I'm suspicious about that. And then finding alpha bar. So the very first thing is about the path. So obviously you can see we do have two paths. The path number 1, which I'm just going to write it down, then I'm going to tell you which one is which, is going to be GC times GP, which equals to what? 10k divided by s times s plus 5. So where is that exactly? The very path, the very first path is obvious one, the most obvious one is going to be this guy times this one and just the output. Easy, right? So the second path is going to be what is going to start from here, then over here, and it's going to finish, oh yeah, and it's going to be finished at this side. Okay, it's going to finish over here. So this is going to be my second path. Second path is so easy. So because it only have one gain in the way, so it's just going to be 2 itself. Easy. So these are my two paths. Then I have to talk about the loops, which, as you guys know, we do have 3 loops. The L1, don't forget about the negative sign, is going to be negative GP times h1, each as end of the day is going to be negative 1 divided by s plus 5. You know better than me where that is, so I'm not going to waste time. L2, which is going to be negative GC GP times h2, which if you simplify your fraction is going to be negative 10k divided by s times s plus 5. And finally, we do have L3, which was somehow hidden, but it would be just negative GFF, the big guy on the top, I'm talking about this, negative GFF times H2 itself, which is going to be negative 2. So just by looking at it, it means that we do have a long way to calculate this one, but actually worth it. So I do have this one. And another important thing is about the determinant non-touching loops. The way that I just talked about it, I do have 2 loops that are going to be non-touch. This guy and this big guy. So I know for a fact that these 2 guys are going to be non-touching loop. It means that they're going to have some effect over the calculation of what? Of this big delta, which is this one. So delta is going to be 1 subtracted by what? L1 plus L2 plus L3 plus L. Which one was what? We had some kind of the L2 and I'm sorry, we have L1 and L3. If I consider that this guy is L1, by the way, we have L1 multiplied by L3. So if you do the calculation by putting all of these numbers between them, I mean, you can do it better than me. At the very end of the day, my delta, which I'm not going to do it right now, but you can do it, and after that you can check your answers with mine. 3s to the power 2 plus 18s plus 10k divided by s times s plus 5. So this is my big delta that I had it over here. Obviously, we have to talk about other parts. So the very important thing is that finding the delta k, right? So delta 1 means that path 1 touches L1, L2, and L3, because the path number 1 was this guy, and as you can see over here, it almost touches everything. So if I get rid of that, means that everything is gone. So I can say that my delta 1 is going to be 1. But what about the delta 2? The path 2 is going to only touch L2 and L3. So by L2 and L3 means that my path 2, which was this one, is only going to touch this loop and obviously this loop. So L1 is somehow immune. So I can say that my delta 2 is going to be 1 subtracted, but whatever feedback loop that actually is working without related to our path subtracted by L1 itself is going to be 1 subtracted by -1 divided by s plus 5, which at the end of the day I can write it down as s plus 6 divided by s plus 3. So the way that I see it, we do have everything that we need. So as you guys can see, for my main formula, my TK, which is going to be gain for my some kind of forward path, the T1, which is going to be first gain, is going to be this. My T2 is going to be this. Then my delta 1 is 1 and delta 2 is 2. And then I do have my big delta, which is going to be like this one. So at the end of the day, if you put all of those information there, your final TS is going to be what? 2s to the power 2 plus 12s plus 10k divided by 3s to the power 2 plus 18s plus 10k. Just imagine that if I would like to find this number with normal way, how much time it would take. Obviously, I did it so fast because I had the answers. You can see that if you would like to do the calculation yourself, it would take a little bit more of time, but it's completely worth it, guys. Believe me. So another thing that we have to see, which I'm not going to solve any question related to that for the future, probably I'm going to talk about a couple of more examples if we do have time, and obviously if you guys need it. Another thing would be about the disturbance mapping, because maybe some of you would say that, okay, at this point, you didn't consider the disturbance. What is happening? Because we had our input, and then we do have the set point, that's some kind of the junction, and then we just move to the end. But what would happen if I do have the disturbance? At this point, I'm going to consider another path which only contains the D as the input itself. So how we can solve this, or how we can find the disturbance response, is that the system is going to determine the delta remains identical, that big delta that we do have, and we simply is going to define D as the new input. Trace, and after that we have to trace a new forward path to see and apply the exact same formula. It's not that kind of the big deal, but you can see that instead of just combining the D by the very first part, try to solve it with 2 paths, and at the end of it you can combine all of them together. Probably next some kind of for the next chapter I'm going to solve a question related to that, but not right now. Right now at this point we are going to talk about a very important slide, which is an error trap radar. Obviously, if we are talking about the Mason rule, there are so many places that you can have some faults, and at the end of the day you just find that, okay, my answer is fantastic, but no, there's something missing. The very first one is about the hidden loop. If you guys remember, for the last question we had a loop that actually wasn't there at the very beginning, but after that, after diving down a little bit inside the question itself, we already found it. So the hidden loop would says that the missing local feedback entirely. Maybe at some point you see one thing and say that, okay, this is just a forward path. It's not very important, but yet that forward path can be combined with another loop, which at the end are going to make another hidden loop itself. Another thing would be about the sign drop. As I just told you, it is very, very, very important about the sign of the loop while you're considering in your work itself. So never forget about that. So your sign, which is going to use it for a calculation, should be negative. Another thing, we do have the ghost pair, and we see that claiming touching loops and are non-touching loops. For example, at this point, you see that these two guys are completely touching because they do share the same node, but you would just tell to yourself, okay, they're not touching, they don't touch each other, but yeah, actually they do. So don't forget about that to consider this. Another thing would be about the forward path that cannot revisit the nodes. Again, remember that. The forward path cannot do it. The forward path only move forward, no backward. And finally, about the delta k default, because this delta k is 1 most of the time, and we just assume that, okay, this is 1, let's get rid of that. No, you have to see that if there is some loops that are going to act unrelated to the forward path, you have to consider them for your delta k. So let's have a little bit of comparison between the block reduction that we had it for the previous chapter and Mason's rule. So when we are going to use the block reduction, most of the time if your system only have maybe 1 or 2 loops, that's going to be intuitive and it's going to be fast. But when your system is complex, you have 3 or maybe more than that of the feedback loops, a couple nested, it's not very feasible. Then the speed, obviously, if we consider the fact that we do have the complex work, speed is going to be slow, but at the end of the day, your some kind of Mason rules is going to be fast, and the error potential is going to be what? For the high, for the order, when you have the order dependent math errors compound, or when your system is complicated by this guy, is going to be low itself. So use the Mason rules as your primary solver for exam and complex field system. It doesn't matter if your some kind of work is going to be have only one or two loops. Yeah, I know it could be a little bit longer than the normal way, but it's trustworthy. And if you have the more than two loops, obviously you just stick to the Mason rules. Use block reduction to visually verify simple subsystems. So it is just intuitive way. It's not that kind of important part. And as you can see in this slide, I put another question for you so you can just read it, and then you can see that how we can solve your question, because in the next episode we are going to talk about the root hertz, and we are going to see that what is going on there and why we use that. So as you guys just saw in this chapter, we talked about a new way which we know it as a Mason's rule. Why we use that way? Because we know not all the time we are going to have a very simple system. At some points we do have two feedback loops. Maybe it's good to use the normal block reduction, but at some point we do have more than that, and there's some point you are very exposed by the situation that you're going to have the error. Why? That at this point it would be better to use the Mason's rule, because again it's more accurate. At some point it's not the fastest way, but at the end of the road you can see is the fastest for the more than two loops, and you can make sure that your system is going to show the transfer function in a way that actually you like. It has a little bit math in it, but it's completely worth it. Again, my name is Mahmoud Kiyosari. Thanks for watching this chapter with me, and after that, if you have any question related to this part, you can put it on the comment down below, and I will be more than happy to give you more examples and solve examples for you, because not only I can teach you guys, I can also learn more things about the control, and obviously at the end of the day about engineering. Have a super great day, night, whatever. See you around.